Problem 26. Okay, I just talked about how to shift functions a little bit. Now we are going to apply that. So here we have downward looking parabola like the usual parabola. So what is this? How does it look like? Like this. This x squared. And it is really easy to follow what we are doing if you use a parabola because you have a specific point, which is the peak, and you can just keep track of the peak. And we are asked to write the equations for all these graphs. For example, let's start with the yellow one. What have we done here? I mean, we are just going to take this and shift it to left by 4, like -4, and then we should shift it down by 1. This is -1. To shift something up or down, we are just doing it like if I have fx like this, fx plus 1 is just that I am taking this, I am shifting it up by 1. And if this is -1, you're taking the graph of the function, you're just shifting it down. So this is the easy part that we can handle. How can we shift a function to left or to right? Again, let's say this is fx. And let's say this is the function that I shifted to right. So what should I write here? Actually, I mean, when we are trying to move the function along the y-axis, like upwards or downwards, what we do is we are adding or subtracting something from the y part of this equation. And to shift it along the x-axis, you should add or subtract something from x. And here, that's why I left it blank. Instead of x, I can write x minus 2, for example. So what will happen? Say this is like the point where x is 0, and this point should have the same value with this, right? So this is like 2. I'm just, let's say, interested only these 2 points, but I mean, whatever we do, it will also apply all the real line. So at this point, what I should get is the original function's value at x equal to 0. When you are drawing this blue graph or this function, what you do is at x equal to 2, you should go to the original function, like f, and you should calculate the value of the function at 0. And you should do the same thing for each point. So that's why if you want to shift a function to right by a, say, which function? So let's say fx, we should just check this function. And if you want to shift to left by a units, then you're just going to add a. Now we can, I think, write all the equations. So for the yellow, shifting left by 4 minus x squared. Instead of that, I will write minus x plus 4 squared. And I also subtract 1 so that we're also pushing it like down. Red one, we are shifting left by 2 units. And also I should add 3. Here we have x minus 1 squared plus 4. And the last one. There are also examples in the book about scaling a function. Like instead of y equal to fx, you are just dealing with y equal to 2fx. What happens then? You are stretching or squeezing the function along the y-axis to make it double. You will see something like this. So when the value of the function is 0, it should again be 0, right? Because making it double, we get 0 again. So it should be something like that. This is fx multiplied by 2, for example. And at each point, what we have is these distances, I mean, they are equal. They are the same. And what else can we do? Instead of this, I mean, you can also calculate 1 over 2 fx be like this, right? So you are stretching either the function along y-axis or squeezing it. So by stretching, this is what I mean. And let me just erase this part. What else are we going to do? We can also consider f2x, for example. What happens if I use the same trick? Instead of the dependent variable, I'm just multiplying the independent variable. This will correspond to squeezing your function along the x-axis. So same value at x is equal to 0. And what else? Let me just also, this was f(x). Let's say this is 1 and this is like 2. So, all right, if I put x equal to 1 over 2 here inside of this original function, what I'm writing is like 1. And in the black function, this corresponds to writing x equal to 1. So when x is 1 over 2, I mean, on the graph of this yellow function, what I should get is the value of the original function at 1. So this point just goes here. And also the same thing happens, for example, in the yellow function. If I write x equal to 1, it's like writing 2 inside the original function. And it is going to be like this. So if I write 2x inside the function, what I do is like I am squeezing the function along the x-axis. And if this is like 1 over 2x, instead of that, I will have this in the value of the function is not going to change when x is equal to 0. So this is like stretching along the x-axis. And there are many examples in the book that you guys can check, and I really recommend you to like do some exercises so that you can feel a little bit comfortable in the exam when you're dealing with functions, because this is what we are going to do like whole semester.